Chapter 13, Sample Problem Number 2. A cart is attached to a spring and is displaced from equilibrium and then released. There is no friction. A graph of the velocity as a function of time for the cart is shown. The arrows and signs above the cart indicate the positive and negative directions for the position of the cart. So we want to know what is the period of the motion for the cart, what is the frequency of the motion of the cart, and which direction was it displaced from equilibrium before it was released. So some of this is going to be just reading from the graph. The period equals time for one repetition. So we pick any place on the graph and find the next identical place. So it's often easiest to go from peak to peak, i.e. this distance, or this length of time, and we can see that that is 8 seconds. As an aside, of course, we could have picked other places. If we went from here to its identical spot is also 8, and from here to its identical spot is 8, and so on. The only thing is by peak to peak or trough to trough is useful because there's only one peak in a cycle, whereas if we take, for instance, the zeros, there are 2 zeros in a cycle, so we have to be careful. But in any event, we get 8 seconds no matter which way we pick. And then the frequency is hard to read from the graph, but is easy once we have the period because the frequency and the period are invert to each other. So this is 1/8 seconds, which we usually write as 1/8 of a hertz. And then finally, in what direction is the cart displaced from equilibrium before it's released? Well, when we displace it, it moves back towards equilibrium. This graph says that when we pull it and release it, it picks up a positive velocity. So it must be in the negative region moving back towards 0. So it must be moving, it was displaced leftward, i.e. toward the negative side, so that it would have a positive velocity when released.